Right now, something enormous is moving through the brightest place in our sky, and we cannot look at it. Tomorrow, October 24, 3i Atlas reaches perfect solar alignment, the sun between us and the target, and the shutters of Earth must stay closed. For more than a week, our telescopes will blink into glare. The decisive moment happens off stage. That is the paradox. Maximum energy, minimum visibility. If you enjoy real investigations, not just headlines, you are in the right place. Tap like, subscribe, and stay with us, because the first clean data after this blackout could change the story. We need to set the board. Solar conjunction means the line from Earth to the object runs straight through the Sunday ground. Telescopes would risk their sensors for nothing but scattering haze. Even space observatories have safety angles and thermal limits that force them to look away. The universe did not schedule this for our convenience, but the geometry feels pointed. 5 days later, on October 29, 3i Atlas swings through perihelion, the point of closest approach to the Sun, exactly when thrust would be most efficient if any thrust exists. Here is the plain language version. Perihelion is the low point in the gravity well, where orbital speed is highest. The Oberth effect, a real workhorse of spaceflight, says a brief push added at peak speed buys you the largest energy change for the same fuel. That is why spacecraft burn near closest approach. If anything wanted to adjust course or shed companions, this would be the smart moment to do it. And because of conjunction, we would miss the act and only see the aftermath when the object reappears in early November. So what are we actually watching for? 3 things at once. First, a position check. Before the blackout, gravity predicts a precise sky path days and weeks ahead. After the blackout, we measure the location again. If the dots line up within the expected error, nothing dramatic happened. If there is a shift that cannot be explained by symmetric venting, the conversation changes. Second, an activity check. Does the plume brighten, rotate, split, or steady as the heating ramps? Third, a structure check. Do we see fragments that drift naturally or grains of light that peel away with purpose? None of that requires faith. It requires patience and a simple scoreboard. We will show how to read it without jargon, where you can look each night, how to compare observer reports, and which measurements are strong versus slippery. You do not need a graduate seminar to follow the next chapter. You need clear terms and honest thresholds. That is our deal with you. We will frame what is known, what is uncertain, and what would actually count as a surprise. Let us also be honest about the emotional undertow. The timing feels theatrical. Conjunction now. Perihelion next. A global audience forced to wait in the dark. It is easy to fill that dark with speculation. Resist the urge to leap. The fastest way to be wrong is to want the answer too much. Curiosity is a better engine. It burns cooler and it runs longer. Here is the watch list we begin building together. Dates you can circle. Instruments to watch for fresh releases. Simple tests that either hold up or fall apart. October 24 through the end of the month is the blind window. Early November is reacquisition and position math. Mid-November brings longer nightly arcs and cleaner spectra. Late December is a corridor flagged by travel time from perihelion if anything separates fast. March brings a Jupiter side check from a very different vantage. You will hear opinions. Some will say comet, end of story. Some will say craft, end of story. Both are shortcuts. We will earn our conclusions the slow way, with measurements anyone can cross-check. When the data drops, we will walk through it together in plain speech, because the night sky is not a rumour mill, it is a laboratory. If the ordinary model wins, say it. If something refuses to fit, admit that too. Either way, the truth pays for your time. We are blind for a moment, not forever. The sky always turns. The glare fades. The dots come back. When they do, we will be ready with the questions that matter, and the patience to let the numbers answer. Stay close. The next part breaks down how perihelion actually changes the physics, and what a natural comet should look like under this much solar fire. Start with the picture your body already understands. You ride a swing. You move slow at the top and fastest at the bottom. If you pump your legs exactly at the low point, a tiny effort adds a big kick. Space does the same trick. Perihelion is the bottom of the swing for an object orbiting the Sunday velocity peaks. A short push here buys more energy than the same push anywhere else. That efficiency boost has a name in astronautics, the Oberth effect, and spacecraft engineers live by it. Translate that into our story. 3i Atlas reaches perihelion on October 29. Solar power on its surface will be higher than at any other time in this pass. Sunlight intensity grows fast as distance shrinks, so the available energy for heating ice, releasing gas, and driving any vent surges. If this visitor is only a natural comet, here is what the next chapter should look like. As the days approach perihelion, the coma brightens gradually. Carbon dioxide and other volatiles stream off the sunlit side. The plume grows, and the classic sunward jet, the tail pointing away from the sun, strengthens as radiation pressure and solar wind push dust and ionized gas outward. Rotation adds texture to that picture. Observers measured a spin near 16 hours. A single hot region turning in and out of sunlight should make the coma breathe on that rhythm, brighten a little, dim a little. The overall envelope still rises toward perihelion, then eases as the object recedes. Under the plain comet model, any side thrust from venting is messy and averaged out. The net effect on the path is small and hard to pick out over a short window. Now, place perihelion within today's geometry. The object is currently behind the sun from our line of sight. Telescopes obey safety angles. You do not point sensitive optics near the solar disk unless you like broken instruments. Even spacecraft with sunshades have keep-out zones. That is why the crucial moment happens off stage. We will not see a burn if there is one. We will not watch fragments separate if any do. We will only read the footprints afterward when the glare eases in early November. So what can still be tested cleanly? More than you might think. Gravity gives us a baseline ephemeris, a forecast of where the object should be, on the sky, night by night, if nothing but sunlight and gravity act. The first reacquisition after conjunction checks this with a ruler. Observers record right ascension and declination against the star field. Stack a few nights and you extract a velocity vector. If the measured path hugs the gravity, only forecast within expected error bars that supports passive behavior. If the path shows a coherent offset in a specific direction, and that offset grows with time, the discussion moves beyond ordinary venting. Thermal physics gives us a second test. As energy input spikes, the spectrum should evolve in predictable ways. If deeper layers of the nucleus warm, water lines tend to grow relative to carbon dioxide lines because water ice requires more heat. If water stays oddly weak while carbon dioxide dominates through and after perihelion, that is a clue that composition or structure is unusual. Polarization is a third check. As particle size distribution changes, the sign and strength of polarized light can flip or drift. A stable negative signature through the hottest period would be noteworthy. Now the fork in the road. Path 1. November positions match gravity within tight bounds. Plume. Chemistry drifts toward water as expected. Any sunward feature fades as geometry shifts, and no coherent fragments appear. The story becomes a natural comet with quirks that new models can probably absorb. Path 2 positions show a directional change that outgassing models struggle to match. The forward collimated feature persists or sharpens, chemistry refuses to track the heating script, or a cluster of points peels away on purposeful trajectories. That does not prove design, but it puts design-shaped questions on the table. A word about patience. Short arcs can lie. One night of astrometry is a tease. 3 nights begin to sing. A week lets the math breathe. That is why early November will feel slow, and then suddenly decisive. Expect preliminary whispers, first small residuals, faint trends, followed by stronger statements as the error bars shrink. We will make those thresholds explicit when the data arrives so you can tell signal from wishful thinking. Perihelion is the bottom of the swing. If the universe plans nothing special, we will see the usual rush of heat and dust and the gentle exhale of a comet turning the corner. If something else is in play, this is the smartest moment to show it. Either way, the physics is clear, the tests are simple, and the calendar is already set. Here is where the story gets weird in a way your brain cannot ignore. On October 13, an observer reported a sequence of light pulses from 3i Atlas that did not look random. 5 bright bumps, then 8, then 13. Those numbers sit on a famous staircase called the Fibonacci sequence, where each step equals the sum of the 2 before it. Nature loves this pattern in shells, sunflowers, storm spirals. Your eye recognizes it even if you could not name it in math class. So what if it is not a camera trick? Let us separate poetry from measurement. A comet can brighten and dim for simple reasons. The surface rotates and a reflective patch turns toward us. A vent opens and sprays dust that glitters for a while. The atmosphere around the nucleus becomes patchy, and the sunlight it scatters flickers as the gas thickens and thins. All of that creates noisy light curves that look lumpy but lack structure. A structured signal is different. It repeats. It carries timing relationships that do not wash out when you smooth the data. How would we test a claimed 5-8-13 pattern? First, independent observers need synchronized clocks and raw intensity measurements through the same filters. That removes color tricks and timing drift. Second, you align the datasets on the sky and subtract background stars and airglow. Third, you look for consistent spacing between peaks, using simple windowed averages rather than aggressive filters that can manufacture rhythm. If the pattern is real, multiple telescopes in different places will recover the same timing within small margins. If it is instrument noise or processing bias, the rhythm will slide or vanish. Now a different tension creeps in. The reported date, October 13, echoes a century-old mass sighting in Portugal, sometimes called the day the sun danced. Tens of thousands reported a strange display at that location on that date in 1917. The match of calendar days is a hook the human mind bites hard. Could it be a coincidence? Absolutely. Does repeating the coincidence make it feel less like coincidence? Also, yes. This is how apophenia works. We see faces in clouds, we assemble clusters from noise. The cure is prediction. The only way a numerically charged story earns respect is by calling a future shot. So let us translate numerology into a clean forecast. If a Fibonacci pattern is being broadcast by physics or by intent, we should see it again when geometry and brightness allow, not only on a single lucky night. The rule we can test is simple. During the next bright window, short pulses should arrive in groups whose counts fall on the Fibonacci ladder more often than chance allows. 5, 8, 13, maybe 21. We can compute how often a random noisy comet would fake such runs. If observations exceed that expectation by a wide margin, the claim survives round 1. There is also a physical middle path. Suppose a rotating jet happens to sweep our line of sight, and the plume breaks into clumps at a natural frequency set by thermal cracking or by the period of the spin. A beat like that can fold into ratios that flirt with Fibonacci counts without any mind behind it. That is why we need timescales. If the separation between peaks scales with the rotation or with the wind of sunlight, we can model it. If the separation locks into number ratios that float free of these drivers, the case for structure strengthens. Here is the part you can help with. Open data matters. If the original pulse train is posted with exact timestamps and filter information, other analysts can try to reproduce it from public sky surveys and from small telescopes with off-the-shelf cameras. The more hands, the better. Good science is cooperative. It rewards replication, and it punishes fragile claims that require secret source to hold together. So, where does that leave us? A single night with a suggestive pattern is a spark, not a fire. The next tests are straightforward. We need repetition across instruments. We need timing that refuses to smear when folded over the rotation period. We need a rate of Fibonacci-length clusters that a Monte Carlo of random comets cannot match. If those boxes check, we have a puzzle the community will not be able to wave away. If they do not, we chalk it up to the universe playing with our pattern-seeking brains again. Either way, the November window will tell us more than any clever argument can. The sky is the judge. We just need to ask clean questions and accept clean answers. So why did the sky go quiet exactly when the questions got loud? A solar observatory paused its public stream on October 13. A government furlough slowed image processing around the Mars flyby. The high-resolution frames many expected never landed in public archives on the timetable people imagined. If you felt the floor tilt from science into secrecy, you are not alone. But there is a second explanation that is messy rather than malicious. Big missions move at the speed of procedures. Here is the unglamorous reality of a modern space camera. First you downlink packets, then you reconstruct them into images. You remove hot pixels and cosmic ray hits. You apply flat fields and dark frames. You calibrate the pointing so every star is exactly where it belongs. Finally, you build the metadata so other scientists can trust every number down to the last decimal. That takes people, time, and checklists. When staffing thins or systems hiccup, the pipeline clogs. It feels like a blackout. It may only be a backlog. Now lay that against our story. A solar telescope that usually streams almost continuously experiences a technical pause on the same day someone reports a curious pulse pattern from 3i Atlas. It comes back later, but the gap is real. A Mars orbiter with a famously sharp camera flies past the best geometry we will have for a while. A government furlough hits at the worst moment. Public-facing websites stall. Preliminary characterizations appear in interviews before any calibrated frames are posted. If you are an optimist, that is awkward timing. If you are a skeptic, that feels like narrative control. So what is fair to expect? It is reasonable to want raw frames quickly with a clear label that says not yet calibrated. It is reasonable to want a timetable for when cleaned products will arrive. It is reasonable to want the processing recipe made public, so anyone can repeat the steps and check the numbers. Those simple promises rebuild trust even when teams are swamped. Silence does the opposite. Silence breeds theories. Let us also be precise about what a missing image would actually change. A high-resolution Mars flyby frame would not solve every mystery in one shot. It would give a bright pixel or two that constrain the nucleus size. It would tighten the mass estimate and either make the giant hypothesis breathe easier or gasp. It would show whether the inner coma looks compact or ragged at tens of kilometers per pixel. None of that answers intent. All of that answers scale. Scale matters because a very large object is harder to nudge with natural venting and easier to keep on a clean track through perihelion. There is a path through this that does not require faith. Watch for 3 kinds of releases. First, prompt roars with honest caveats. A folder of unpolished frames helps the community test ideas while the official pipeline works. Second, calibrated images with full metadata. Look for exposure time, gain, plate scale, and pointing solution. If you can read a flexible image transport system header, you can verify the basics yourself. Third, technical notes that show the intermediate steps. When teams publish the recipe, not just the cake, arguments get quieter. What about the solar observatory gap? Glitches happen, storage rolls over, ground stations go down. None of that would be remarkable on a random day. It becomes remarkable when it overlaps with a claimed anomaly. Here is the antidote. Post the downtime log with times and causes. Post the first and last good frames around the gap. If there were planned calibrations or safing events, say so in plain language. The truth is usually boring, and boring truth beats exciting mystery every time. A final word on briefings without data. Institutions often try to get ahead of the story with words. They mean well. They do not want the public to spiral. But describing an observation as ordinary before you show the evidence is like reviewing a movie from the trailer. It may be right. It is definitely unsatisfying. The cure is simple. Speak when you can show. If you have to speak, early, set a short fuse on the data release and keep that promise. We do not need villains to make this chapter dramatic. We need clarity in the place of vagueness. We need dates on the calendar instead of soon. We need a habit of posting not only pictures, but the map that proves where and how those pictures were taken. Do that, and the room calms down. Do that, and even if 3i Atlas turns out to be ordinary, the process will have earned our trust. The gap will close. Streams resume. Archives fill. When they do, the next question is not who hid what. It is what the pixels actually say about size, mass, chemistry, and motion. That is the conversation we came for. So what was that long bright streak in the Martian night sky? A cylinder racing across the stars, or a camera doing exactly what cameras do when a faint point of light slides during a long exposure? Before we build castles on a single picture, let us build a ruler. Astronomers call it angular resolution. It tells you how big something looks on the detector compared to the smallest detail the camera can separate. If the smallest dot the camera can draw is wider than the object itself, the object will never look like a neat shape. It will smear into whatever the camera and the exposure time allow. Think of tracing a sparkler in the dark. If you hold it still, you see a bright dot. If you sweep it fast while the shutter is open, you get a glowing line far longer than the sparkler. Telescopes see the same trick when a target moves during the exposure. The exposure time stretches a true dot into a dash. With navigation cameras and science cameras on Mars, exposure times are often tuned for terrain or starlight, not for a tiny interstellar point zipping across the sky. A few seconds is plenty of time to draw a streak. Now, add plate scale. That is the conversion between angles on the sky and pixels on the detector. If one pixel spans a broad slice of sky, a single pixel of length can correspond to thousands of kilometers at the object's distance. Stack several pixels in a row during a sweep, and the streak looks enormous, even though the real source is tiny. The mind sees length and screams structure. The math whispers motion blur. There is a sanity check anyone can do. Ask what size the nucleus could be from brightness limits made by independent telescopes. Even with a reflective surface on the dim side, the numbers cap the diameter within a few tens of kilometers. Now compare that to the length of the streak when you convert pixels into distance. If the streak would imply a body hundreds or tens of thousands of kilometers long, the answer is already in front of you. It is not a ship the size of a planet. It is a point source dragged by time. Look at another clue. If an image shows a true elongated body, different instruments with different exposures should repeat the shape and orientation. If it is motion blur, Small changes in exposure and tracking flip the length and position angle around. That is what we saw with the Martian frames. The streaks do not agree in a way that argues for a rigid structure. They agree in a way that argues for a moving dot under varying camera settings. So why does this matter? Because the fastest way to fool yourself is to cling to weak evidence that happens to be visually exciting. Throwing out the seductive but unreliable pictures makes the remaining anomalies louder. The forward jet that points toward the Sunday, the chemistry that leans hard toward carbon dioxide and nickel, the missing non-gravitational nudge despite weeks of venting, those are built on multiple nights and multiple instruments. They do not rest on a single dramatic frame. There is also a lesson in humility here. Even seasoned observers can be tripped by context. A rover image feels intimate. It was taken from the surface of another world, so it must be special. In truth, a rover's navigation camera is a workhorse for driving and rover chores. It was not, designed to freeze a fast-moving point in a short exposure. When we ask it to do that, we push it outside its sweet spot, and the sensor gives us artifacts that human brains love to misread. Here is how we keep ourselves honest the next time a streak goes viral. Check the exposure time. Check the plate scale. Check whether the camera tracked the stars or the horizon. Check for matching images from other instruments with different settings. If the shape is real, it will survive those checks. If it is not, the glamour dissolves quickly and we move on with sharper questions. There is no shame in being excited by a beautiful image. Wonder is the fuel of science. The trick is to burn wonder clean. We can admire the streak and still recognize it for what it is. A point source that walked across a sensor while the shutter was open. A reminder that pictures can sing and mislead in the same breath. We lose nothing by letting this one go. In fact, we gain something essential. We narrow the case to the signals that resist simple explanations. That is where the story earns its mystery. Not in a single ambiguous line on a single night, but in patterns that keep returning when the instruments change, and the nights change, and the people holding the data change. Those patterns are coming up next. Imagine a campfire whose smoke flows into the wind, not away from it. That is how the forward feature around 3I Atlas first felt. Comets usually wear their tails like capes blown back by sunlight and the solar wind. Dust and ionized gas stream away from the sun, forming classic anti-solar plumes. But repeated images from different observatories showed a slender glow stretching toward the sun, narrow and straight, with a length roughly 10 times its width, a tail where no tail should be. Could geometry fake this? Sometimes Earth crosses a comet's orbital plane and a sheet of leftover debris lines up edge-on. That perspective can draw a spike that appears to point ahead, even though the grains are really coasting behind the nucleus along the orbit. The fix is careful geometry. You correct for viewing angle, clock the position of the sun, and ask whether the feature stays put as the Earth-Comet-Sun triangle changes. In this case, the forward spike held steady across different dates and different angles, more than you would expect from a fragile perspective trick. Now, layer in rotation and chemistry. Observers clocked a spin near 16 hours. A vent locked on a single patch of the surface should rotate in and out of sunlight every half turn, about 8 hours. That should make the forward plume pulse or curl into a spiral as the nozzle swings. Instead, the feature looks stubbornly collimated, like a beam with only gentle breathing. Spectra added an odd twist. The gas around the object was rich in carbon dioxide and comparatively poor in water, even far from the sun where many comets slumber. Carbon dioxide wakes early, water usually needs more heat. The mix suggested a surface or subsurface that did not match the snowball template we teach in classrooms. So what could drive a sunward jet? One natural possibility is large, slow dust grains lofted from the warm face. Big grains feel less push from sunlight. They can hover forward for a while before pressure, and the solar wind herd them aside. Pair that with a spin axis tilted, so the same face keeps meeting sunrise, and you can sketch a forward-leaning spray that looks like a jet. Another possibility is a narrow vent that acts like a nozzle, focusing gas and dust into a pencil beam. If the vent sits near a pole that points roughly at the sun, the beam would not sweep a wide arc as the body turns. Each fix comes with a cost. The tilted axis must sit near a special orientation. The vent must stay active without carving the rotation into a wobble. The grain sizes must cluster just so. You can make it work on paper, but the model begins to collect fragile assumptions. That is why the forward feature matters. It is not impossible. It is not proof of anything artificial. It is a stress test for natural explanations. The more hoops you add, the more the story owes us in predictive power. Here are the clean tests the next window allows. If a vent is pushing hard in one direction, there should be a small acceleration in the opposite direction. That push becomes most important near perihelion when heating peaks. When the object reappears in early November, careful position measurements night after night will reveal whether a coherent non-gravitational acceleration has turned on and which way it points. If the acceleration matches a model of asymmetric venting derived from the jet's orientation, chalk one up for the comet camp. If the position change points somewhere that does not agree with the plume geometry, the model needs new gears. Second, watch the plume's shape as the Sun-object-Earth angle improves. A perspective artifact should morph quickly as geometry swings. A true collimated outflow should keep its direction relative to the Sun and change length smoothly with heating. If the beam fades while an ordinary sunward jet grows, the forward feature was likely a transitional phase tied to a specific temperature band. If the beam persists alongside a normal tail, that is rarer and demands a linked physical story rather than a one-off trick. Third, follow the chemistry through the peak. If deeper layers warm, water should rise relative to carbon dioxide. If water stays weak while the forward feature remains crisp, we are looking at a structure or composition that keeps behaving like itself, even when the cookbook says it should change flavor. This is the kind of puzzle science loves. The answer hides in geometry, timing, and patient measurement, not in a single dramatic frame. The tail that points the wrong way challenges us to earn our explanation. In a few weeks, the sky will tell us which version survives. Contact with new data. Here is a curveball you can taste on your tongue. The light from 3i Atlas is not only bright, it is colored by elements. Split that light with a spectrograph and you get barcodes. In comets, nickel and iron tend to appear together because they live in the same mineral grains. Heat a grain and both metals escape in roughly linked amounts. But observations around this visitor show strong nickel lines with iron either faint or missing. That is not the usual song. It is a lonely instrument playing without the band. Could nature do that? Maybe. But let us translate why the eyebrows go up. In the lab and in industry, there is a known pathway where nickel is separated cleanly from impurities. You flow carbon monoxide gas across warm nickel. A vapor compound forms that carries nickel away. Later, you heat the vapor and it breaks apart, leaving purified nickel and releasing the gas. It is an elegant trick used to refine metal. The key point for our story is simple. The process tends to prefer nickel over iron. So, when astronomers see a plume rich in nickel and oddly poor in iron, the analogy writes itself in people's minds. Still, analogies are not proofs. Before we whisper technology, we ask what natural furnace could mimic that preference. One idea is temperature zoning. Suppose certain patches on the surface reach a narrow thermal range, where nickel-bearing compounds release easily, while iron stays locked in tougher grains. Another idea is size sorting. If the vented gas carries a specific grain size out of the nucleus, and if those grains happen to be nickel-friendly, the plume could skew toward nickel for a time. A third idea leans on long exposure to space. Cosmic radiation can restructure surface chemistry over millions of years, maybe creating weird reservoirs that vent in unexpected proportions when warmed. All three require the right knob set just so. Temperature bands must stay stable on a rotating, cracking surface. Grain sizes must somehow avoid iron. Companions. Radiation must rewrite layers in a way that just happens to favor nickel. None of that is impossible. But when a single measurement asks for many special conditions at once, scientists push for more measurements. So, what would help? Time series spectra, before, during, and after perihelion. If nickel to water and nickel to cyanide ratios evolve smoothly with heating, the signal might be a transient chemical phase that fades as deeper material wakes. If nickel stays high, while other indicators swing as expected, that strengthens the case that the source is specific and stubborn. Spatial information helps too. If a narrow region near the sunward side dominates the nickel lines, a vent with special chemistry becomes plausible. If nickel glows in a halo on both sunward and antisolar sides, with the same shape as ordinary molecules, the process looks more global and harder to explain away. There is also a simple cross-check with dust. If nickel is being produced from solid grains rather than gas phase reactions, polarimetry and scattered light should betray changes in particle makeup. Negative polarization paired with nickel-rich gas would hint that particle surfaces are strange, perhaps metallic or coated in a way not common among garden-variety comets. If instead the dust behaves normally while the gas goes odd, the mechanism sits in chemistry rather than grain physics. Now the speculative question you are already asking. Could a non-natural object produce a plume that looks nickel-rich and iron-poor? Yes, in principle, if it were processing metal on board or venting byproducts of a system that handles nickel differently from iron. But principle is not evidence. To move beyond mood, we would need a package of signatures that line up together, not one taste on the tongue. A deliberate velocity change inconsistent with modelled venting. A pattern in radio or optical light that repeats with intent. A thermal map with hotspots that refuse to track sunlight. The nickel puzzle is a powerful data point, not a verdict. So here is our test for the coming weeks. If the object is simply a complicated comet, the nickel anomaly should relax toward ordinary ratios as perihelion comes and goes, or at least correlate cleanly with vents we can see. If instead, the anomaly deepens when the energy peaks, and if it stays high while other molecules behave off script, we will have to widen the hypothesis set. Either we will discover comet chemistry we did not know we needed, or we will be staring at a signal that keeps pointing past geology toward engineering. This is where restraint earns dividends. Let the spectrum talk. Let it talk across nights, across telescopes, across distances. If the nickel solo keeps playing while the iron section sits silent, the next parts of this story will not be shy. Picture a leaky balloon whizzing around a room. Gas blasts out one side, the balloon jerks the other way. Space plays by the same rule. When a sunlit surface vents gas and dust, momentum leaves with the plume, and the body should twitch off its gravity-only course. Astronomers have watched this tiny non-gravitational shove on many comets. It is subtle, but over weeks the path drifts just enough to measure. With 3I Atlas, the shove did not show up. The track hugged the gravity forecast through months of active venting. There is a simple way to square that circle. Make the object heavy, very heavy. If the plume pushes with a certain force, and the acceleration we measure is force divided by mass, then a larger mass drives the acceleration towards zero. We know the venting rate is not trivial, because telescopes have measured the output of carbon dioxide and other gases. We also have reasonable speeds for that outflow from similar comets. Multiply mass per second by meters per second, and you get a thrust. If the sky path still refuses to bend, the denominator must be big. That implies a minimum mass in the tens of billions of tons, and a hard, floron size of several kilometers across. Those numbers are startling because our census of interstellar visitors is tiny. The first one we found looked like a sliver, maybe a few hundred meters at most. The second was a more ordinary comet, perhaps a kilometer across. Now the third is at least several kilometers wide and maybe larger. That is like catching your first fish with a hand line and the third cast netting a whale. Possible, yes. Likely, no. Standard models say little bodies are far more common than giants, and giants are much harder to throw out of their home star systems intact. Mass changes more than statistics. It changes the choreography near the Sunday. A light rubble pile is easy to talk. A heavy, coherent body is harder to twist. A light comet with patchy vents can spin up, tumble, and wander under its own exhaust. A heavy one shrugs and keeps steady time. The measured rotation near 16 hours fits that vibe. Steady spin. No clear sign of the kind of chaotic torques that send weaker bodies wobbling. That steadiness does not prove anything beyond inertia, but it rhymes with the heavyweight picture. A larger mass also reframes the sunward jet puzzle. If a vent is truly focusing material forward, the equal and opposite push should nudge the body backward. For a light nucleus, that push would appear quickly as a drift against the gravity ephemeris. For a massive nucleus, the same push takes longer to show. That is why the early November position checks matter so much. If we finally see a coherent offset after perihelion, we can try to match its direction and magnitude to the geometry of the forward plume. If the fit is good, asymmetric venting earns credit. If the fit is poor, the model needs new scaffolding. There is a second lever, mass pulls, and that is fragmentation. Weak, small comets often crack near peak heating and centrifugal stress. Pieces drift apart at modest speeds, meters per second, and the swarm stretches into a string. A large monolith, or at least a tightly bound aggregate, is more resistant. If 3I Atlas cruises through perihelion with no debris field and the light curve stays smooth, that again suits the heavyweight picture. If it breaks sharply into multiple parts, the community will study the separation speeds and directions for clues about structure and internal strength. So, how do we corner size from the sky? One path is a high-resolution image that resolves the core, or at least delivers a saturated central pixel bright enough to bound the area. Another is careful photometry across phase angles, using how the brightness changes with sun-object-Earth geometry to tease out the surface reflectivity and the footprint that would create the observed light. Both methods have uncertainty, but together, they corral the answer into a range. If the lower bound on size climbs, while the upper bound from brightness stays generous, the case for a giant tightens. Heavy does not mean artificial. It means rare and stubborn. It means a body that keeps its rotation clean, resists its own exhaust, and carries enough inertia to turn the perihelion chapter into a slow reveal rather than an instant tell. That is why patience is not a luxury in this act. We are timing a freight train, not a bicycle. Here are the plain tests that follow from mass. If positions after the blackout track gravity almost perfectly for another month despite strong heating, then either vents are well balanced or the nucleus is truly massive, or both. If a clean, steady, non-gravitational acceleration appears and points opposite the forward plume, asymmetric venting gets a boost, and the minimum mass can be refined. If fragmentation occurs, separation speeds and brightness of the pieces will tell us whether the parent was a weak pile or a tough block. Mass is the quiet character in this story. It does not flash in a single frame. It accumulates its argument step by step as the sky offers us new arcs and better angles. When we speak about extraordinary possibilities, we should let this character speak first. Heavy things are hard to fool. If the heavyweight walks through perihelion as if nothing happened, that is a clue. If it lurches, that is a different clue. Either way, the numbers will not lie. Picture the solar system as a thin vinyl record. Most planets ride the grooves of that record, circling in almost the same flat plane. Now imagine an interstellar traveler diving in from any direction in three-dimensional space. Most such paths should slice the record at steep angles, skim across, and leave. 3i Atlas instead slides almost flat along the record, within only a few degrees of that planetary plane, and it does it while moving backward compared to the direction the planets flow. Flat and retrograde, that combination makes the stage crowded with potential encounters. Let us translate the jargon. Inclination is the tilt of an orbit relative to the planetary plane. Low inclination means the path hugs the plane. Retrograde means it flows opposite to the planets. Thread a flat, retrograde course through the inner system, and you do not need to chase worlds. They approach you. Close passes become more likely simply because the geometry puts you in the same busy traffic lane at the right time. That is what happened near Mars, and similar opportunities open with other worlds as the months roll on. Could this be random? Yes, rare things happen, but rare becomes interesting when you stack it with timing. The arrival did not just graze the plane. It did so at a moment when the geometry set up meaningful passes. That is how planetary mission designers think when they plan gravity assists. They do not brute force with fuel. They choose lanes and times that let planets donate momentum for free. Seeing a natural visitor slip into a lane that mission designers would admire is not proof of anything, but it does raise the eyebrow. There is another layer that has fueled conversation. Decades ago, a radio telescope in Ohio recorded a narrowband signal from the direction of Sagittarius that never repeated. The team circled the numbers on a printout and wrote a single excited word in the margin. Ever since, people check that patch of sky for echoes. The approach direction for 3i Atlas lies within single-digit degrees of that historical beam. The sky is huge. Single-digit degrees is a slender slice. Coincidence is possible, but coincidences that touch iconic waypoints collect attention, and attention demands cooler heads. Here is how to keep our balance. Geometry can be gorgeous and still be natural. A flat path can fall out of a random distribution once in a while. Retrograde motion can happen without intention. The question is whether the path also begins to act like a plan. Plans predict, plans pick targets. Plans leave footprints that fit deliberate choices better than thermal burps and chance alignments. That is why the next weeks matter more than any goosebumps from a tidy diagram. Start with encounter timing. If this is simply a comet on a lucky route, the passes should look like skims that add up to nothing but good photo ops. If it is something else, we might see course tweaks that refine future passes, the way a mission designer trims a trajectory after a burn. Those tweaks would not need to be loud. Even a small nudge near perihelion can shift a meeting by millions of kilometers weeks later. Our job is to measure whether the shifts line up with a pattern rather than a shrug. Then there is the question of targets. A natural fragment cloud would spread along the orbit, like breadcrumbs blown by the same wind. A designed fan would send pieces on diverging lines that point towards specific worlds. Watch how any new dots behave after the blackout. Do they remain a tidy string, or do they splay like fingers reaching for different keys on the piano? The sky will answer with simple angles and nightly motion. Finally, revisit that historic, the radio direction with discipline. If the approach angle lined up by chance, nothing else should care. If the angle matters, you might look for narrowband emissions when the geometry favors detection. This is not a promise, it is a test. You tune the dial, define the window, listen, and report what you find, even if the answer is silence. Silence is information. It shrinks the space where speculation can sprawl. So could a flat, retrograde, encounter-rich trajectory be an accident? It could. Could it be a choice? It could. The only way to tell is to stop narrating our hopes and start checking the score. Where is the object after perihelion? How do the small changes add up? Do the passes tighten into a pattern with a purpose, or do they dissolve into the background noise of celestial mechanics? The record is spinning. The needle is down. If there is a melody here, the next bars will reveal it. Could we be fooling ourselves because strange things are easier to notice and more fun to share? That is selection bias in a nutshell. The sky is full of boring visitors we never see. Our surveys mostly catch the bright, the close, and the odd. Then our minds multiply small probabilities like raffle tickets and call the jackpot impossible. The trouble is that many of those probabilities are not independent. Tilt, timing, brightness, detection method, all tug on each other. Multiply them naively, and you turn a long shot into a miracle without meaning to. Let us slow the math down to walking speed. Suppose you say the chance of a flat approach to the planetary plane is small. True. You say the chance of retrograde motion is also small. True. You say the chance of a convenient pass by Mars is small again. True. If those were dice rolled at different tables, you could multiply. In reality, a low tilt increases the chance of encounters with planets that live in that plane. Retrograde motion changes relative speeds and encounter opportunities. These features are linked. The product, time of their odds, is not the right way to judge surprise. Add the spotlight problem. We did not find 10,000 interstellar objects and then pick the weirdest one. We found 3. The third is bright and interesting, so we pointed every telescope and opinion at it. The more you look, the more patterns you will see, some real and some not. That is why strong claims need guardrails that hold even when attention is intense. You do not judge the story by the most exciting paragraph. You judge it by predictions that land on schedule. There is also the small sample curse. With 3 data points, the universe can mock your averages. You can have 1 sliver, 1 ordinary ice ball, and 1 heavyweight, and still be staring at random variety. In a decade, when we have 100, the curve will look different, and the oddballs will find their proper place. Until then, humility is a feature, not a flaw. It keeps us from drawing straight lines through noise. So how do we keep curiosity without getting conned by our own pattern hunger? We make a clean standard of proof, and we stick to it. The standard has 3 parts. First, prune aggressively. Throw out the weak pictures and the single night wonders. Keep only signals that survive new instruments, new angles, and new analysts. Second, anchor surprise to a model. If an anomaly demands 5 special conditions to fit the natural comet box, it should also offer at least 1 specific forecast that can be checked next month, not next decade. Third, price in the bias. Ask whether the same selection rules that made the object visible also made certain oddities more likely. Judge the remainder, not the whole pile. Concrete examples help. The forward jet is surprising. The clean test is a directionally consistent acceleration after perihelion that matches the jet geometry. That prediction does not care about social media volume. It cares about nightly sky positions. The nickel without iron is surprising. The clean test is a time series that shows whether the ratio tracks heating and vent locations in a way chemistry can carry, or whether it stays stubborn when everything else changes. The heavy mass is surprising. The clean test is whether months of strong venting continue to leave the path glued to gravity, or whether a delayed nudge finally appears and how large it is. Now, flip the coin. What would make us step back and say, our excitement was selection talking? If the forward feature melts away, exactly as geometry and temperature models predict. If nickel relaxes toward ordinary comet ratios as deeper layers wake. If the post-blackout positions sit right on the gravity, only ephemeris within, expected errors for weeks. If fragments, should they appear, string neatly along the orbit with drift speeds in the usual single digits of meters per second, that is what ordinary looks like when you measure it with care. There is one more trap to avoid. After the fact narrative. Humans are gifted storytellers. We stitch meaning into events once the dust settles, then convince ourselves we saw it coming. The antidote is a paper trail of forecasts written before the data lands. That is what we are building together in this series. Not a mood board, but a list you can grade. If the sky checks our boxes, we accept it. If it does not, we update. No drama required. Coincidence is not a dirty word. It is a real part of a large universe in a small sample. Bias is not a sin. It is a lens that we can correct when we know it is there. The job is to keep both in view while we test the claims that matter. Come early November, the numbers will start talking again. We will listen with our excitement dialed up and our multiplication of odds dialed down. The first clean night after conjunction is not a celebration. It is a measurement. We do not ask what the object is. We ask where it is. Gravity has already given us a forecast. Astronomers call that an ephemeris. It is a night-by-night map of where a passive traveller should, to appear on the sky. We will point our telescopes to those coordinates and see if 3i Atlas shows up on cue. If it does, the story stays calm. If it does not, the plot thickens. Here is how the check works in plain language. Each exposure pins the object against the fixed pattern of background stars. From that pattern, we extract right ascension and declination. Think of them as latitude and longitude for the sky. 1 night gives a position, 2 nights give a line, 3 nights start to reveal a track. Stack a week of clean measurements, and you can measure a small drift that gravity alone cannot explain. That drift is what astronomers call non-gravitational acceleration. It is the footprint of a push. We separate push from noise by being boring and careful. First, we correct for the atmosphere. Starlight wiggles when air ripples. That wobble can move a point by a fraction of an arcsecond. Good reduction routines tame it. Second, we correct for the camera. Every detector has tiny quirks, hot pixels, slight distortions. Those must be mapped out so the same star lands in the same place each night. Third, we timestamp every frame with precision. A late clock will lie to you about speed and direction. The cure is a global time source and disciplined logging. Now the scoreboard you can follow without a lab course. The gravity-only forecast gives a predicted position each night with small error bars. Observers post measured positions with their own uncertainty. Subtract one from the other and you get a residual. Plot that residual as a function of time. If the dots hop around 0 with no trend, nothing unusual is happening. If the dots march in a direction that grows steadily, a real acceleration is at work. The direction of that march matters. If the forward jet is a true vent pointed sunward, the body should feel a push opposite that direction. The residual should point accordingly. If it points somewhere else, the vent story must evolve. Brightness. Evolution adds a second layer to the test. The days around perihelion pump energy into deeper layers than before. If ordinary comet behavior dominates, the spectrum should shift as water wakes up. Stronger water lines. Ratios that migrate toward familiar values. Polarization might also drift toward the more common positive signature as particle sizes change. If instead the chemistry stays locked in its earlier odd mix while the position also drifts in a coherent way, then we are looking at a pattern that resists the easy path back to normal. What about fragments? Reacquisition nights are when we look for a spray of faint points near the main glow. Natural breakup tends to produce a string of pieces that share almost the same path. They separate slowly at a few meters per second and stretch like a necklace. A purposeful deployment would look different. Pieces would fan out on diverging lines. Over several nights, the geometry would stop looking like a tidy string and start looking like a hand opening. You do not need complex math to tell those pictures apart. A few overlays from one night to the next will do. Small telescopes can help here. You do not need a mountaintop to contribute. What you need is consistency. Same optics, same filters, same cadence. Calibrate your images against star catalogs and post your numbers with the details of your setup. Citizen science tightens error bars simply by adding nights that professional facilities cannot spare. Many weak links can still make a strong chain if they are honest about their limits. Expect the first week to feel tentative. Residuals will be small and easy to overread. The second week brings confidence as the noise averages down. By the end of the month, we should know whether the path is glued to gravity or slipping a little in a specific direction. We should also know whether the inner structure looks calm or complex. Patience is not a delay here. Patience is part of the instrument. If the positions hold and the plume behaves, textbook normal, the case for a quirky but natural comet grows. If the positions slide with intention and the plume keeps its forward spine while chemistry refuses to follow the heating script, then we have a cluster of signals that ask for a bigger explanation. Either way, the score will be on the board where anyone can read it. When comets fail, they do not explode like movie spaceships. They sigh apart. Heat opens, hairline cracks, rotation tugs. Gas squirts through pores and widens the faults. Then the nucleus sheds pieces that drift like dandelion seeds. The speeds are gentle, a few meters each second, and the pieces trail the parent along nearly the same road, spacing out into a lazy string. That is the signature of natural breakup. Slow, parallel, predictable. Now picture a different scene. A parent body reaches peak energy near the sun and smaller objects separate with purpose. Not a string, but a fan. Not one drift speed, but several, each chosen to bend into a different lane. The dots no longer trail one another, they diverge toward destinations. You do not need insider schematics to tell those stories apart. The sky will draw the geometry for you. Start with the physics of a rubble pile. Weak aggregates fail when three stresses align. Thermal stress from sunward heating drives expansion and contraction across fractures. Centrifugal stress from rotation adds a steady outward pull. Faster spin, greater pull. Reactive stress from venting applies little rockets all over the surface in shifting directions. None of these forces care where Earth is. They care about sunlight and the body's own layout. That is why natural fragments remain in formation. Everyone is riding the same freeway, nudged by the same winds, separated by small, nearly parallel differences in speed. If 3i Atlas follows that script, the map in November and December will be familiar. A core and a string of companions. Each point moves roughly in the same direction night after night. Separation grows at a steady, modest rate. The sunward jet broadens as smaller dust is pushed back by sunlight and the solar wind. Spectra of the fragments look like the parent, give or take brightness, because everyone is sampling the same interior recipe of ice and dust. A deploy scenario writes a different map. Separation vectors would not align. One piece leaves a little above the orbital plane, another leaves below it. A third slides inward toward the Sunday, a fourth outward. Over a week, the pattern stops looking like beads on a thread and starts looking like a hand opening. The separation speeds are larger, climbing beyond the sleepy single digits that rubble piles can generate. You might even see timing linked to geometry, with release near perihelion when the Oberth advantage makes small pushes go a long way. Light curves also behave differently. A natural fragment brightens as fresh surfaces sublimate, then fades as the hot crust thickens. A purposeful object might show steadier or more erratic patterns uncorrelated with simple heating. One could dim, while another brightens even though both sit at similar solar distances. Thermal maps, if we can get them, might reveal hotspots that ignore the sun's sweep, a clue that energy is being managed rather than absorbed. We can test this without special badges. Track each candidate fragment's position night by night and fit a simple line for its sky motion. If all the lines point the same way with similar slopes, that is a string. If some lines diverge like spokes from a hub, that is a fan. Measure angular separation over time. If it grows linearly, at a lazy pace, think rubble. If it grows faster, with different rates for different pieces, think more carefully. Try low-cost spectra on the brighter fragments. If their signatures match the parent closely, that favors a single source of exposed material. If one fragment shows chemistry that is out of family, that asks harder questions. There are boundary cases, worth keeping in mind. A strong outburst can fling chunks in a messy spray and still be natural, especially if the nucleus fails catastrophically. That will look chaotic at first. The tell is the long game. Even chaotic sprays from a single breakup settle into an elongated cloud stretched along the orbit. The apparent fan collapses into a string. A true deployment stays fanned and keeps separating in several distinct directions. Do not expect instant clarity. The first nights after conjunction will be noisy. Glare and short observing windows will limit how many fragments we can tag. Patience pays off quickly here. By the end of the first 2 weeks, the geometry will either relax into the classic necklace or sharpen into a splayed hand. By late December, separation distances will be large enough that even small telescopes with careful calibration can contribute clean vectors. There is no shame in hoping for a tidy story. The universe often gives us the complicated version. Our job is simple anyway. Watch, measure, plot. Strings point to breakup. Fans point to deployment. If the sky draws a hand opening towards several worlds, we will say that out loud. If it draws a necklace and drapes it along a cold road out of the inner system, we will say that too. Either way, you will see the shape with your own eyes. Comets, in the story we teach, are dirty snowballs. Water is the main ice. Carbon dioxide and carbon monoxide are extras that wake earlier because they boil at lower temperatures. When a typical comet cruises inward, carbon dioxide whispers first and water shouts later as the heat digests deeper layers. 3i Atlas flips that rhythm. Carbon dioxide is loud. Water is strangely quiet. Cyanide lines are stronger than you would expect if water were doing the heavy lifting. The chemistry reads like a menu printed upside down. Let us translate what those molecules imply. Carbon dioxide turns to gas far from the Sunday. If you detect a vigorous carbon dioxide plume at POW, large distance, the surface or near surface must be rich in that ice, or cracks must expose reservoirs that were kept cold and ready. Water needs more heat. It tends to surge later, near and after perihelion, as sunlight penetrates deeper. If, as the energy ramps, water still lags badly behind carbon dioxide, something about the structure is not textbook. Either the water is locked away under a protective layer, or much of it is simply not there in the first place. There is a natural path to a carbon dioxide-heavy crust. Imagine an object spending millions of years drifting between stars, its skin sandblasted by cosmic rays. Radiation can split molecules, drive hydrogen off the surface, and leave behind carbon-rich residues. Over time, that processing can dehydrate the top layers, turning water into other compounds and leaving a rind that vents carbon dioxide easily, while water remains buried or consumed. If fractures are shallow and do not pierce the rind, the spectrum would lean toward carbon dioxide even as heating climbs. Another natural path is birthplace. If 3I Atlas formed in a region far from its star where temperatures were low and nebular chemistry favored carbon dioxide ice loading, the bulk recipe might start carbon dioxide rich. Ejection from that home could have preserved the mix, especially if the body is large enough that internal heat never rearranged its inventory. In that case, the current spectrum is not a temporary crust effect. It is a fingerprint of origin. Now add cyanide. Cyanide emissions often trace organic chemistry in comets. When ultraviolet light breaks apart larger molecules, cyanogen appears in the glow. Strong cyanide alongside weak water is unexpected, because pathways that enrich organics often coexist with reservoirs that release water as well. The mismatch hints that we are sampling a layer that has been chemically cooked in a special way, rich in complex carbon molecules, lean in water ice, or that gas phase, processes above the surface of boosting cyanide signals compared to the familiar family of comets. There is a third, spicier angle. If the nickel anomaly holds strong nickel without the usual iron chorus, then the chemistry and the metal lines are both playing off script. A model that explains one, but not the other, is incomplete. A model that explains both earns respect. For example, a protective crust altered by radiation could preferentially trap iron-bearing minerals in larger, heavier grains that do not escape easily, while letting certain nickel carriers and carbon dioxide out. That is speculative, but it is the right kind of speculation. It ties two puzzles to one physical story that can be tested. What will perihelion teach us? Heat drills deeper. If buried water exists, the lines should strengthen, as sunlight carves into layers the crust could not insulate forever. Ratios of water to carbon dioxide should rise, even if slowly. If water remains a faint murmur while carbon dioxide keeps roaring through and after the peak, the case for an intrinsically water-poor body grows. Polarization adds another thread. If the dust grain sizes evolve as deeper material is exposed, the sign and magnitude of polarized light should drift in step. A stable negative polarization paired with stable water weakness would mean we are not simply skimming a temporary frosting. We are seeing something more fundamental. We can set clean thresholds. If, 2 weeks after perihelion, water lines triple relative to carbon dioxide, we are likely watching a thaw that finally reached buried ice. If the ratio barely moves while total brightness changes with geometry, the crust and bulk composition are probably carbon dioxide heavy. If cyanide keeps punching high while water stays low, that combination demands either an unusual organic matrix or a gas phase route we have not modeled well. Could this chemistry be engineered? Perhaps, in principle, if material were processed to liberate certain gases while suppressing others. But principle is a wide country. Evidence is a narrow road. To walk that road, the chemistry would need to align with other signatures, trajectory changes that look planned, thermal patterns that ignore sunlight, or deliberate emissions in radio or optical bands. Until then, the honest story is that the water is missing where we expect it, the carbon dioxide is bold, the organics are loud, and the simplest tests are on the calendar. The sky will answer without drama. Either the water wakes up on schedule and the comet playbook stretches to cover this case, or it does not, and we write a different chapter. Keep your eye on the ratios. They are the plot. Take off your sunglasses for a moment. Polarized lenses cut glare because scattered sunlight is not random. It favors certain directions. Comet dust does something similar. When sunlight bounces off a fog of tiny grains, the electric field lines in that light line up more in one orientation than another. Most comets give what astronomers call positive polarization, a specific alignment relative to the sun object observer plane. 3I Atlas breaks that expectation. Multiple measurements report negative polarization, the flip side of the usual signal. It is as if the sunglasses suddenly make the glare brighter instead of dimmer. What makes polarization flip? In simple terms, particle size and surface properties. Very small grains, far smaller than the wavelength of visible light, can scatter in ways that invert the usual pattern. Certain coatings or compact metallic surfaces can also twist the alignment. Geometry matters too. At tiny phase angles, when sun, object, and observer nearly line up, some bodies show a shallow negative dip before swinging positive at larger angles. But comets tend to share a family resemblance in these curves. When an object strays far from that family, ears perk up. Let us translate this into a mental picture. Imagine a cloud of flour versus a cloud of glitter. Flour grains are tiny and fluffy. Glitter flakes are larger and reflective. Shine a light, and the two clouds throw very different sparkles back at you. Polarimetry is a way of measuring those sparkles precisely. 3i Atlas looks more flour than glitter in the sign of its polarization, yet other clues point to a jet that is tight and a chemistry rich in carbon dioxide, with nickel lines stronger than iron. That mix is not impossible. It is just unusual to hold all at once. So, what natural routes can take us to negative polarization? One route is an abundance of ultrafine grains, freshly produced by cracking and abrasion near the surface. Another is a high fraction of very porous aggregates, clumps of tiny particles that act optically like sponges, trapping and re-radiating light in ways that flip the polarization sign. A third invokes a mantle of complex organics that coats grains and modifies their scattering behavior. Each route predicts different behavior as heating changes and as the viewing angle sweeps through new geometries after conjunction. Here is the testable part. If ultrafine grains are the cause, the negative polarization should relax toward positive, as those grains are blown away and larger particles dominate, especially after perihelion when outgassing peaks. If porous aggregates drive the effect, the sign could persist, but the magnitude should respond to changes in gas flow that fluff or compact the dust. If organic coatings matter most, polarimetry might correlate with spectral signs of carbon-bearing molecules, a chemical and optical duet rising and falling together. This is not just a curiosity. Polarization helps cross-check the nickel and water puzzles. If the dust environment is dominated by ultrafine particles, you expect certain thermal and photometric behaviors, faster fading after outbursts, stronger forward scattering glows that can be measured alongside spectra. A persistent, negative polarization paired with a long, collimated sunward feature would be especially provocative, because collimated jets often carry larger, more ballistic grains that tend to push polarization toward the positive family. If the sign stays negative while the jet stays needle-thin, the dust story must be more intricate than a simple nozzle blasting sand. We also have geometry on our side. As the object emerges from behind the sun, the phase angle will change night by night. That provides a built-in sweep across the polarization curve. If 3i Atlas behaves like a standard comet in disguise, the curve should bend toward the familiar positive regime at moderate phase angles. If instead it doubles down on negative values across a broad range, we will be compelled to look beyond standard dust recipes. Citizen measurements can help here too. Polarizing filters are not exotic. With calibrated cameras, amateur observers can measure relative intensities through different orientations and contribute to a global phase curve. The key is consistency. Same instrument, repeated nights, careful logs. Professional observatories can tie the scale. The world can fill in the cadence. Could an artificial source engineer a dust cloud that flips polarization? In principle, yes, by releasing ultra-fine or specially coated particles, but principle is cheap. The real question is coherence. Do we see polarization behavior that tracks a controllable pattern independent of sunlight, or do we see responses that dance with heat and geometry the way natural dust does? If the polarization swings with the sun, nature is the prime suspect. If it holds oddly steady across changing angles while other signatures hint at purpose, that is a different conversation. For now, treat negative polarization as a loud question mark that sits next to the forward jet and the nickel-rich spectrum. If a single natural model can explain all three with the same set of grain sizes, coatings, and vents, it deserves the microphone. If the pieces keep resisting a shared story, we widen the hypothesis set. Either way, the sky is about to give us a cleaner phase sweep. Watch how the sign changes or refuses to. The alignment of light itself is telling us what kind of dust is in that glow. Numbers have charisma. 16.16 hours for a rotation period feels too tidy. Convert it to minutes, and you get 969.6. Someone notices that 969 echoes an ancient age from a sacred story. Someone else divides by the length of an Earth year and finds a ratio close to a golden value that artists rave about. The brain lights up, it wants meaning. Pattern hunger is a survival trait. It also tricks us into hearing music in static. So here is our line in the sand. Coincidences that appear after the fact do not get to sit at the adult table. If a number matters, it must help us predict the next thing the sky will do. Otherwise, it is trivia with great lighting. That sounds harsh. It is actually liberating. It frees us to enjoy clever connections while refusing to wager our credibility on them. Start with the rotation. A true spin period shows up in the light curve because different faces of the nucleus reflect different amounts of sunlight. If the period is real, folding many nights of brightness data on 16.16 hours should stack the peaks and valleys neatly. If the peaks smear, then either the period is wrong, the shape is more complex, or vents are repainting the curve faster than the object turns. A genuine harmonic also tends to show side notes at half or one-third the period when geometry or multiple jets modulate the signal. These are mechanical tests. They do not care about poetry. Now, graft the Fibonacci claim onto this. If pulses counted as 5, then 8, then 13 are more than a story we told ourselves once, we should catch the same structure again when signal-to-noise climbs after conjunction. The rule is simple. Count pulse clusters over a fixed window and compare how often Fibonacci lengths appear versus other lengths. Do it with blind bins chosen before you look, not with bins nudged after the plot is made. Then ask a tougher question. Do the cluster lengths line up with a fixed fraction of the rotation, or with a thermal timescale tied to sunrise on the surface? If yes, physics is in charge. If no, something else is poking the rhythm. We also have to guard against the kitchen drawer problem. If you open enough drawers, you will find a spoon that matches any dish. In data terms, that means if you try many filters, many smoothing windows, many start times, and only show the one that sings, you can fake structure from noise. The cure is pre-commit your recipe. Choose the filter width, the detection threshold, and the counting window before the next observing run. Write it down where others can see it. Then run exactly that on the fresh data. If structure survives, it earns respect. If it evaporates, the draw trick was doing the work. Here is a clean way to do that together. 3 teams on 3 continents agree on a simple pipeline. Same band pass, same exposure cadence, same noise cut. Each team posts raw light curves with timestamps and flats. A small group that is not part of any team runs the agreed analysis. The output is a stack of folded curves and a plain count of cluster lengths with a baseline from simulated noisy comets. We will know in a day whether the staircase keeps appearing or whether it was a one-night fever dream. There is a deeper reason to be strict here. If we let numerology drive, it will steer us into every mirage on the map. If we keep it on a short leash, it can still be useful. Patterns that really exist can hint at mechanisms we did not include in our first models. A jet that pulses on a clean schedule might point to a vent locked near a pole. A beat that shifts with distance from the sun could point to thermal cracking with a well-behaved timescale. Those are stories you can test in December and beyond. A final reminder to our future selves. Meaningful numbers predict, decorative numbers entertain. Both have a place in human life. Only one belongs at the center of a science investigation. If you feel a neat ratio tugging at your curiosity, smile at it. Then ask it to name a sky position, a pulse time, or a shift in a spectrum before the shutter opens again. If it cannot, thank it for the spark and move on. In the next part, we leave the realm of private spreadsheets and step into the machinery of institutions. How big missions handle messy data can look like fog from the outside. We will clear that fog without dark conspiracies and without naivety, because trust is built the same way numbers are tested with steps you can check. From the outside, science looks like a light switch. One day nothing, next day headline. Inside, it is closer to a factory floor with checklists, handoffs, and tools that only run when safety lights are green. That is why big missions can feel slow, right when the world wants speed. The pace is not about hiding, it is about not breaking the thing you built for a decade to capture a moment you cannot repeat. Start with the pipeline. Spacecraft send down packets, not pretty pictures. Teams rebuild those packets into frames, then chase out hot pixels and cosmic ray hits. They align the star field so the geometry is right. They attach the numbers that let other people trust the result. Every step has a person in the loop who signs off that the previous step did not introduce a new error. If the team is short-staffed or the network hiccups or a clock drifts, the line slows. You do not skip steps to go faster, because a fast wrong answer costs more trust than a slow correct one. Now, the culture. Government labs and space agencies are allergic to premature claims. They were burned before. A few noisy mistakes can haunt a mission for years. The response is caution. Draft, review, second review, then release. That caution is not tailored to social media time, which is measured in minutes. When a mission says soon and soon turns into weeks, the public imagines smoke where there may only be paperwork. Here is how to bridge the gap without asking anyone to bet the mission. First, announce timelines in calendar dates, not in vague words. If the team needs 2 weeks to move from raw to calibrated, say it and add the 2 milestones in between. Second, post the raw files with a banner that says not calibrated and include a short README that lists known artifacts. The community can explore while the official pipeline runs. Third, publish the recipe. The steps, the corrections, the version numbers. When the public can repeat the cooking, the cake earns trust. Fourth, separate narration from evidence. If a spokesperson gives a characterization before data drop day, they should also give the date and promise the files that back it up. Better still, point to a single page that will hold every release so people do not chase rumors. Fifth, embrace independent replication early. Invite a small outside group to run the same reductions from the same raws and post their numbers in parallel. That is how weather services and particle physics labs protect themselves from tunnel vision. Astronomy can do the same when a case turns hot. There are also communication traps worth dodging. Do not call an observation ordinary before you show the plot that makes it ordinary. Do not tease with pretty but ambiguous images when the interesting part is still in the queue. Avoid phrases that imply closure, while the most relevant products are not yet public. Clarity beats comfort. If a shutdown slowed the pipeline, say so. If a sensor needed a reset, say that too. Most people can handle boring truth. What they cannot tolerate is silence that stretches past a promised date. The public also has a role. Curiosity needs discipline. Demanding instant answers can push teams toward shortcuts that backfire. The right pressure is for transparency in schedules and shared methods, not for speed at any cost. When teams meet those requests, give credit loudly. Reward the behavior you want to see again. A healthy feedback loop is built from both sides. How does this apply to 3i Atlas? The next month is a perfect chance to reset habits. Post a reappearance calendar that lists expected windows for astrometry, spectra, and polarimetry. Share the exact fields of view so amateurs can contribute to cadence. Release any high-resolution frames with their headers intact, and a short note on what those headers mean in normal speech. If a gap occurs, publish a log with times and causes, even if the cause is a dull server issue. Dull is good. It means the sky, not secrecy, is in charge of the drama. Trust is not a slogan. It is a ledger that fills with small, timely, verifiable steps. If institutions make those deposits now, the community will stay patient through the parts that must be slow, and when the data finally lands, we will be ready to argue about the only thing that matters here. What the numbers say. Here is how we stop being spectators and become part of the instrument. The sky is big. Professional telescope time is small. But thousands of modest rigs working with the same habits can turn a handful of snapshots into a movie with real power. Think of it as a relay. Each observer carries the baton for a few minutes under their weather and hands clean numbers to the next station further along Earth's longitudes. The result is a continuous track that shrinks error bars and exposes trends a single mount will miss. Start with aim and timing. The only question that matters on night 1 is where and when. Use the latest public ephemeris to pull a target list measured in right ascension and declination for your location. Print the list so you are not fishing on your phone in the dark. Sync your mount, focus with a bright star near the target, and lock your clock to a reliable time server before you leave Wi-Fi. A wrong minute is a wrong velocity. A wrong second can smear a short exposure when the target is fast. Now set your exposure plan. Short and steady beats long and dramatic. You want points, not streaks. Pick a cadence your mount can hold without guiding drift. 10 or 20 seconds is often the sweet spot for faint comets with small scopes. Shoot in a single broadband filter or clear, because color games can hurt more than they help at this stage. The prize is a sequence with honest timestamps and stars that match a known catalogue down to a snip of an arc second. Calibrate as if someone will check your homework, because they will. Take darks at the same temperature as your lights. Take flats that flatten the vignetting. Build a master bias if your camera needs it. When you reduce, keep your steps simple and write them down. Subtract the master dark. Divide by the master flat. Align on the stars, not the comet, for astrometry. Align on the comet for a separate stack that helps people see the coma and any companion points. Post both, they answer different questions. Astrometry is where small telescopes punch way above their weight, solve each frame against a star catalogue. Report the measured position and its uncertainty with the time at mid-exposure. Do not round more than the camera earns. If your plate scale is rough, say so. Honesty about limits makes your data more valuable, not less. A coordinator can downweigh a noisy point. They cannot fix a number that pretended to be better than it was. Photometry and polarization are the next rungs once you have your astrometry rhythm. For brightness, choose a few nearby comparison stars that are not variable and measure their flux in the same aperture you use for the comet's center. Record sky background levels. Report relative brightness changes rather than absolute magnitudes if you are not fully calibrated. The shape of the light curve matters more than the exact zero for many tests. For polarization, a simple rotatable polarizing filter can give a first hint, but be careful. Take matched exposures with the filter at 2 or 4 orientations and keep the same focus and framing. Record the angles precisely. Expect small differences that are easy to fake by accident. Post the raw intensities and let others compute the derived signal. That transparency protects the community from chasing ghosts. Fragments are where patience pays. If you think you see a companion point, do not chase it with adjectives. Pin it with positions on 2 nights. If it moves with the main body, it is likely a fragment. If it sits on the sky while the comet slides past, it is a background star. When in doubt, blink 2 aligned frames from different nights. Your eye is great at spotting motion when the field stays still. Coordination is oxygen, a simple shared sheet that lists observer, location, aperture, filter, exposure, and seeing will prevent duplication and fill gaps. Rotate coverage across longitudes so the object is watched for longer arcs each 24 hours. When clouds win in one region, another can pick up the thread. That is how you turn a patchwork into a single instrument that spans the planet. Most important, separate story from score. Post numbers first, discuss later. A clean table of positions and times can be ingested by anyone and tested against the gravity forecast within hours. If the residuals begin to walk in a direction, the world will see the same walk no matter what story they brought to the field. That is the power of an open watch. We will keep folding your data into the same simple charts every few days. Sky position versus time, brightness versus time, polarization versus phase angle. If the object behaves like a comet with quirks, those plots will show it. If it decides to write a different script, those plots will show that too. Either way, a global watch turns waiting into doing. You will not just hear what happens, you will help measure it. Circle 2 dates on the same page. Early November for reacquisition, late December for consequences. The corridor between them is where the story either cools into a better comet model or ignites into something stranger. Think of November as calibration and December as verdict. By the second week after conjunction, nightly positions will reveal whether the path hugs gravity or drifts. By the 4th week, spectra and polarization will show whether chemistry and dust behave like a thaw or cling to their anomalies. Then the calendar flips to the month when small changes made near the sun grow into big separations in space, begin with distance and geometry. Mid-December, 3i Atlas reaches one of its better observing positions for Earth even if it is still far. That is when long nightly arcs let us nail the velocity vector with confidence. If there was any thrust at perihelion, the offset should be measurable by then, and its direction should mean something. A push opposite a persistent sunward jet would support asymmetric venting. A push that points somewhere the plume does not would force a new mechanism. At the same time, the viewing angle improves for dust studies. A forward feature that was marginal in August and September will either fade as ordinary tails dominate, or stay stubborn as the heating script says it should not. Now layer in travel time. If anything separated fast near perihelion, the 60-day rule of thumb puts late December in the arrival window for close passes to inner worlds. Natural fragments would still be clustered, stretched along the parent path like a necklace. Designed releases would have fanned out. That is the picture to watch for. A few bright points diverging from the main body toward clear destinations is not something you need a doctorate to recognize. It is obvious in a simple overlay from one week to the next. Chemistry should tell a parallel story. If water was merely hiding under a processed rind, December lines ought to climb as deeper layers participate. Ratios of water to carbon dioxide should trend upward, not down. Cyanide should behave like a fellow traveler, not an unmoored outlier. If nickel remains loud while iron stays quiet, the case that this plume is not a copy of familiar comets strengthens. If nickel relaxes toward the family, the industrial echo dulls and the natural inventory wins around. Polarization is the quiet referee. Negative values across a broad sweep of phase angles would be extraordinary. A flip from negative to positive, as geometry changes, would fold 3i Atlas back toward the known family. If the sign stays negative, while a narrow forward jet also stays needle-thin, we will owe the dust a more complicated story than standard grain size distributions can easily supply. December offers a clean sweep of angles to test exactly that. Communication speculation will bubble as the holidays approach. The disciplined version of that speculation is simple. Define narrow windows when the geometry is best for listening, and publish the bands and times in advance. Then report what you heard, even if it is silence. Silence is not a disappointment, it is a constraint. It boxes in the space where wild ideas can wander, and makes the remaining questions sharper. Through all of this, remember the scoreboard we have built together. Positions first, chemistry second, dust third. Pictures are for context, not for verdicts. If December brings quiet numbers that match the gravity forecast and the cookbook of comet physics, the extraordinary narrative will give way to a better ordinary one. If December brings a coherent offset, a stubborn forward jet, nickel that refuses to share the stage with iron, water that stays oddly shy, and polarization that keeps its sign when it should not, then we carry a very different package into the new year. There is an emotional trap at the end of the corridor. Late month dates carry cultural weight. It is easy to let that weight paint meaning onto the sky. Resist it. The calendar does not care about our traditions. The test is the same on any day. Predict, observe, compare. If something real is happening, it will ignore our storytelling and still leave footprints in the data. If nothing unusual is happening, it will also ignore our storytelling and flatten into a lesson about how patient measurement wins. So we walk the corridor with our eyes open and our thresholds clear. A week of strong astrometry, a week of deep spectra, a run of polarimetry across changing angles. That is enough to tell whether this act ends with a bow or a twist. Either way, the night sky will not waste your attention. It pays you back in answers if you do the work. The inner system gives us heat and glare. The outer system gives us perspective. In March, 3i Atlas sweeps past Jupiter's neighborhood, and two things become possible that Earth alone cannot do. First, parallax. Observers near Earth see the object from one angle, while a spacecraft in Jupiter's realm sees it from another. With two viewpoints, small ambiguities in speed and direction collapse. Second, diagnostics. Instruments riding with the giant planet listen and look in parts of the spectrum our ground telescopes barely touch. If there is anything to hear or feel beyond reflected sunlight, Jupiter's corridor is where we might catch it. Think of Juno, the Jupiter orbiter, as a scientific eavesdropper. It carries a radio and plasma suite that reads the electric and magnetic weather, an ultraviolet eye for auroras, and an infrared mapper for heat. The Jupiter Icy Moons Explorer, a European mission nicknamed JUICE, carries its own mix of cameras and spectrometers. Neither craft will fly right next to 3i Atlas, but both can point their sensors and take the solar system's temperature at a new angle. If the visitor is only a comet cooling off, these instruments should see a fading glow and a dust environment that behaves like tired fireworks. If it is something less simple, the signatures could be odd in ways that are hard to hide. Start with the easy wins. 2 vantage points turn a flat line of positions into a 3-dimensional track. If Earth-based astrometry in November and December hinted at a small non-gravitational shove, March lets us check whether that shove persists or fades as the object cools. A thrust produced by natural venting should drop as sunlight weakens. A thrust produced by something controllable might change in ways that do not care about distance from the Sunday. Earth's dots and Jupiter's dots plotted together will tell the difference with less guesswork. Now the thermal story. A comet's skin obeys sunlight. The day side warms, the night side cools. As spin turns surfaces in and out of light, temperatures ebb and flow with a rhythm tied to that rotation. Infrared maps that show hot spots locked to terrain rather than to sunlight would be strange. Hot zones that keep their brightness as the object recedes would also be strange. Neither would prove design, but both would lean away from simple ice and dust. A cold, natural nucleus should look like a lumpy rock wrapped in a thin, cooling atmosphere of gas and powder. No tricks, no surprises, just a steady slide toward quiet. Radio is where imagination runs ahead of evidence, so we pin it down. The disciplined play is to define bands and windows before listening, then publish the result either way. If narrowband emissions emerge that repeat in a pattern, we take that seriously and ask whether they line up with any spin harmonics or geometry changes. If the radio sky stays silent within those windows, that silence is not a disappointment. It shrinks the playground for wilder ideas and presses us back toward chemistry, dust, and dynamics. Jupiter itself helps in another way. The giant's magnetic field and plasma environment are noisy. A cloud of dust and gas that is merely drifting will leave one kind of trace in that weather. A body that pushes against its path will leave another. Subtle perturbations in plasma flow and energetic particles can betray how much material is being shed and whether that shedding is steady or spiky. Match those traces to optical changes, and you get a cross-check most comets never receive. Geometry will have improved too. By March, the phase angles are different, which means polarization can be sampled again from a new arc without waiting years. If the negative polarization reported earlier was a trick of angle, the sign should flip here. If it holds across the sweep, we owe the dust a model that behaves the same in the cold as it did near the heat. That kind of stubbornness is rare. Rare is not impossible, but rare demands clarity. Trajectory designers will be watching for something else as well. Jupiter is the solar system's most generous banker of momentum. A passing body can win or lose speed with a small change in aim. A natural object on a hyperbolic escape will barely notice unless it dives deep. A guided object could use even a modest pass to reshape where it goes next. You will not see a dramatic turn. You will see downstream encounters shift by just enough to look like a choice rather than a coincidence. That is why we keep all the geometry in view past, present, and planned, and ask whether small changes line up into a coherent itinerary. None of this requires faith. It requires clocks, coordinates, and the discipline to compare what heat and fields say to what light and dust say. If everything points to cooling ice and fading plumes, the Jupiter chapter will be quiet in the best way. If any map refuses to follow sunlight, that is a headline, not because it screams aliens, but because it forces us to admit that our pile of natural fixes is no longer buying what the data is selling. March is not the climax. It is a mirror that reflects whatever truth November and December start to reveal. If the story is ordinary, the mirror will show a comet coasting into the dark. If the story is stranger, the mirror will show a pattern that does not care which side of the sun we stand on. Either way, we will read it the same way we have read every chapter here, with patient instruments and questions that do not flinch. Here is the uncomfortable arithmetic. Most strange things in the sky turn out to be natural once the data piles up. That is the base rate, but once in a long while, a low probability event with high impact walks onto the stage and refuses to leave. Risk people call that a black swan. You do not bet your house on swans of any colour. You also do not ignore the pond if someone whispers they saw one. The trick is to prepare rationally without feeding panic, and to set proof bars that are high enough to protect truth but not so high that they erase warning signs. Start with asymmetry. If 3I Atlas is a quirky comet, the cost of over-preparing is small: some telescope time, some paper drafts, a few red faces. If it is not, the cost of under-preparing could be ugly, from blown scientific chances to scrambled institutions. That imbalance argues for serious watching, even when the odds of extraordinary outcomes are low. We do not alarm our neighbours. We do the work a little earlier and a little more thoroughly than comfort demands. Now, draw a clean ladder of evidence. Rung 1 is kinematics. A coherent, sustained offset from the gravity-only path after perihelion, measured by multiple teams, with direction and magnitude that do not fit any reasonable venting model, earns a flag. Not a conclusion, a flag. Rung 2 is structure. A forward jet that remains thin and sunward, while a normal sunward jet also grows, matched to dust behavior and polarization that do not relax toward the family of known comets, earns another flag. Rung 3 is chemistry. Nickel lines that stay strong while iron stays weak, across changing heat and geometry, plus water that he remains shy when it should be bold. Stack the flags higher. Rung 4 is dynamics of fragments. A splayed hand of diverging tracks, with speeds and directions inconsistent with a single natural breakup, is no longer a curiosity. It is a demand for explanation. Rung 5 is energy. Thermal maps that show hotspots careening past the logic of sunlight, staying bright while the object recedes, speak in a language that chemistry alone struggles to translate. Rung 6 is communication. Narrowband signals that repeat with geometry or timing patterns earn the rarest flag of all. None of these rungs alone force a verdict. Together, they sketch a picture you cannot wave away with a shrug. How do we keep our heads if flags begin to stack? We set thresholds now, not after the excitement. For kinematics, define a minimum offset beyond combined errors and a required duration. For dust and polarization, define the range of phase angles and magnitudes that would count as abnormal across several instruments. For chemistry, define ratios and changes we expect from a thaw and how far outside those ranges a result must sit before we call it anomalous. For fragments, define separation speeds that exceed rubble pile physics by a clear margin. For thermal maps, define how far a hotspot may drift from the subsolar point before we use the word independent. Preparation is more than thresholds. It is logistics and language. Logistics means standing agreements for telescope time if certain triggers fire, so nobody is hunting for slots while the window closes. It means a short list of analysts who can drop everything and run the same reductions on the same data to check each other quickly. Language means a shared glossary for public updates. Words like drift, fragment, and anomaly should carry the same meaning in every release, so the world is not left to decode jargon while rumors outrun facts. There is a civic layer too. Strange sky stories attract fear and fantasy. The cure is daylight. If a team hears something on the radio or sees a new dot near the main body, the first move is to tell other teams where to look and how to check. That keeps the narrative honest. It also keeps anxious imaginations from filling the silence. You do not have to explain everything in the first hour. You do have to say what you saw, when you saw it, and when you expect to know more. What does success look like in black swan math? It looks boring. It looks like strong measurements that confirm a natural comet with unusual chemistry and dust, a good paper on carbon dioxide, heavy crusts, better models for forward jets, and a global watch that proved its worth without catching anything beyond physics. What does failure look like? It looks like missing the moment because thresholds were fuzzy, coordination was late, and trust leaked out faster than data came in. So we write the plan now, while our pulse is steady. We define the triggers, we pre-write the checklists, and we point the microphones at the people who will share numbers first and narrative second. If the swan is just a goose in bad light, we will still have built a better pond. If it is not, we will have earned the right to be surprised without being caught flat-footed. Let us be adults about the wild card. What if November and December do not quiet the story? What if the path drifts in a way venting cannot carry, the forward jet refuses to relax, nickel keeps shouting while iron stays silent, and a few objects peel away on clean lines toward real destinations? What if, on top of that, a narrow band tone shows up on a schedule you can set your watch to? Not a rumor, not a meme, a repeatable thing measured by more than one team. We do not panic. We pull the playbook off the shelf and read aloud. First principle. Verification beats volume. If a signal or a maneuver appears, 3 independent confirmations make it real. 1 optical, 1 radio, 1 dynamical if possible. Clocks must agree. Coordinates must be shared. Quiet channels open first so teams can check before the world does. Within hours, raw data and recipes go public so anyone can replicate. That is how you keep trust when adrenaline is high. Not with adjectives. With plots different people can make from the same files. Second principle. Communication tries must be simple, slow, and safe. If a repeating tone appears, you answer in plain math. A prime number count, a binary ladder, a slow sweep across frequencies that avoid stepping on protected bands. You transmit from multiple sites with known antennas and known power levels, then you stop and listen. You log everything and publish the plan in advance. You do not improvise poetry at the microphone. You do not spam the sky. 1 careful call and a long listen tells you more than 1,000 noisy shouts. Third principle. You protect the science while you protect the public. That means clear language from trusted messengers. Daily bulletins with numbers first. Residuals from gravity models. Spectral line ratios. Polarization signs and phase angles. No mystery adjectives. No secret briefings without matching data. If something is unknown, you say unknown. If a timetable slips, you say why and reset it with dates. Silence is where fear breeds. Clean uncertainty is where calm lives. Fourth principle. No cowboy moves. There is no planetary defense switch you can flip that changes the physics of a fast approach. Interception at interplanetary speeds is a fantasy with current hardware. The smart play is observation and preparation, not heroics. You use the time to map trajectories, size any fragments, and watch for thermal patterns that might hint at intent. You prepare ground networks and sky surveys for higher cadence. You protect satellites by planning safe modes if needed. You do not dramatize, you plan. Fifth principle. You widen the circle without losing coherence. Invite laboratories that do not normally watch comets. Invite gravitational wave folks to check their feeds for anything coincident. Invite neutrino detectors to mark the times. Most will see nothing. That nothing is gold. It tightens the narrative and walls off noise. At the same time, you keep a single hub for releases so the world is not forced to assemble a jigsaw puzzle from 1,000 social posts. The human part matters too. If this turns into the chapter that science fiction promised, it will touch beliefs and fears. Religious leaders, educators, artists, and community organizers will be asked to make meaning faster than anyone is comfortable with. The right answer is to slow the drumbeat. Remind people that the sky is not a courtroom that demands instant verdicts. Invite curiosity and patience. Encourage local watch nights that pair wonder with method. Wonder is an ally when it walks with restraint. What counts as proof in this scenario stays exactly the same. Coherent kinematics that exceed venting models. Persistent chemistry that will not join the family of known comets. Dust behavior and polarization that break the usual curves across wide angles. Thermal maps with hot spots that ignore sunlight. Signals that repeat when geometry says they should and vanish when geometry says they must. If those boxes tick, labels will follow. If they do not, the world will still have learned how to turn a noisy mystery into a clean measurement. A final word to future you. If the lights blink back, breathe. Then check the clock and the coordinates. Write down what you predict the next frame will show. When it arrives, grade your own forecast. That is how you stay human in the middle of a history lesson. You make a promise to reality, and then you keep it, even if it rewrites your favorite story. Here is where we land after months of noise, wonder, and patient math. A verdict worth living with does not pretend the universe is simpler than it is. It keeps two ideas in the same hand. First, most mysteries relax into nature when the data gets good. Second, once in a while, the data refuses to relax. Our job is not to guess which way 3i Atlas will fall. Our job is to build a path that makes either answer honest. So, we keep the scoreboard in front of us. Positions first. If the post-perihelion track hugs gravity through November and December, the heavyweight still looks heavy, but not guided. If a steady offset appears and points exactly opposite a persistent sunward jet, asymmetric venting earns the point. If the offset points somewhere that the jet cannot carry, we move the flag up the pole and ask harder questions. Chemistry, next. If water climbs as deeper layers wake while carbon dioxide eases from loud to normal, if nickel calms and iron returns to the chorus, the industrial echo fades. If nickel stays bold while iron stays shy across changing heat and angle, the echo grows louder than comfort. We do not declare meaning. We log ratios, watch trends, and let time do the arguing. Dust and light follow. If the strange polarization flips with geometry and the forward feature broadens into a familiar tail, the dust story joins the family. If polarization keeps the wrong sign across a wide sweep, while a needle-thin sunward plume persists, we admit that our grain recipes need new chapters. That is not failure. That is science doing what it does when nature refuses to fit an old box. Fragments last. If a necklace of pieces strings along the road and drifts with sleepy speeds, that is a breakup. If a fan of dots peels off on clean diverging lines toward different lanes, that is something else. No spin needed. The sky draws its own arrows. A verdict we can live with also respects process. Institutions will do better when they post raws on time, publish recipes, and give dates instead of hints. The community will do better when it rewards transparency and patience more than drama. Citizen observers will do better when they post numbers first and stories after. We can choose that culture. We can choose it today. Let us also be clear about fear. There is none in measurement. If December brings nothing but a tidy comet with odd chemistry, we will have built better tools, better habits, and a new respect for carbon dioxide, heavy crusts, strange polarization, and sunward plumes that look like paradoxes until they do not. That is a win. If December brings offsets that will not fit venting, chemistry that refuses to relax, dust that keeps breaking the curves, and fragments that do not behave like a breakup, then we step onto a different road with the same calm rules. Predict, observe, compare, publish. Either way, your part does not shrink. Point the small scopes, solve the frames. Count the photons, share the files. If you do not own a telescope, you still have a role. Help push for open releases. Help keep the conversation clean. Help your friends separate pictures that wow from plots that decide. The most powerful instrument in this story is not a mirror on a mountain. It is a global habit of honesty that turns 1,000 small efforts into a single clear view. If 3i Atlas finishes this chapter as a natural visitor, We end with gratitude for an object that forced us to sharpen our thinking. If it refuses the natural script, we end with gratitude for a community that met history with humility instead of heat. Both endings are good endings. Both leave us stronger. So here is the final promise. We will not tell you what to feel. We will tell you what the numbers say. We will show our work. We will call coincidence when coincidence is enough, and call anomaly when the data stacks past comfort. We will let the sky write the plot, line by line, night by night, and when the verdict arrives, we will live with it, not because it flatters our hopes, but because it earned its place. That is how science keeps faith with reality. That is how a mystery becomes knowledge. That is how a world learns to look up and stay steady, even when the cosmos leans close.